Welcome to Lecture 7 in Vehicle Propulsion Systems. This lecture will be about KERS, that means Kinetic Energy Recovery Systems, and non-electric hybrid propulsion systems. Before going into the details of this lecture, we start with a short repetition about the key topics we have covered so far. You have seen parallel hybrid electric vehicles where we have two parallel energy paths, where we have one state in the QSS framework, that's the state of charge. You have also worked with the serial hybrid, where we have one path and the operation is decoupled through the battery so that we get two states in the QSS framework. We have the state of charge as a state, and then we have the engine speed as a free variable to select. Hand-in assignment number 2 was about deterministic dynamic programming and developing the energy management controllers to analyze what's the optimal behavior. This is, as I have said, the crown jewel of the course. With deterministic dynamic programming, you are guaranteed to get the global optimum within the discretization. The solution methodology is non-causal, which means that you require full knowledge about the mission, but as you have seen with the series hybrid, it takes quite some time to solve. The further in dimensions you get, we have the curves of dimensionality. The solution time is proportional to the length of the cycle, number of discretization points. If we in each dimension d have n points, the complexity of the total problem is n squared to the power of d. So here we have an exponential growth in complexity with the dimensions that we would like to have in the problem. Normally, deterministic dynamic programming is used for 1 up to 3 dimensions. Deterministic dynamic programming is the reference tool used for prototype development and comparisons due to the properties that it guarantees global optimum within the discretization. And it is also generic, so you can use more or less any nonlinear model for your vehicle and engine system. The next step that you are working with a hand-in assignment number 3 is to develop analytical solutions to optimal control problems. The core of the problem is that we have a functional that we're minimizing, where we have an integral and possibly an endpoint function. We have the differential equation for the system. With this information, we create a Hamiltonian from optimal control theory that puts the time continuous parts into one function called the Hamiltonian. So we put together the cost in the integral and we add mu times our differential equation. And this mu then is a Lagrangian multiplier, and it's a dear child with many names. For example, it's called the Lagrange variable, the adjoint state, the co-state. Most often it's denoted lambda in the text, but mu is also used. To solve the problem, we can use the Hamiltonian. Pontryagin's minimum principle, the theory from Appendix B, shows that when we want to find the optimal control action, it's sufficient to go to a minimization of the Hamiltonian. So the global optimum is the one you get if you at each point minimize the Hamiltonian, provided that you have the optimal mu and you have the optimal trajectory for the state of charge. The necessary conditions for this to be optimal is that the differential equation must be fulfilled and the adjoint variable must follow this differential equation. This is a fairly complex problem to solve for the adjoint state, but if we have a problem that has some properties, the problem can be simplified, and that's the case for hybrid electric vehicles. Especially if this derivative disappears, so that this derivative is 0, then it means that mu dot is 0, so mu becomes a constant and we can update that constant while driving. The reason why we have this case for hybrid vehicles is that the battery characteristics is fairly flat. As function of state of charge, as function of Q here, the output voltage does not change, so this derivative vanishes, and that's a great help for the solution. In your hand assignment you will work with the ECMS, which is another name for using the Hamiltonian. You are given the optimal lambda and you set up the Hamiltonian for your system where you have the fuel power and you have the electric power, and then you take out the optimal control action as a minimization of this. You guess what the optimal lambda is. You run one cycle and see the end state of charge, and if the end state of charge is not the same as it was initially, then you update lambda and you iterate until you get charge sustenance. Then you have found the optimal solution to the problem. Now we come to the new topic for today, which is short-term storage. And we have 3 examples of short-term storage, and this is something you can work on in hand-in assignment number 4, which is non-mandatory. We can look at short-term storages where a flywheel is the storage. We can look at a hydraulic accumulator, or you can use an electric system where a supercapacitor is used as electric storage. When this course was developed, there was a lot of talk about short-term storages for Formula 1 circuits. In 2009, FIA allowed the usage of 60 kilowatt kinetic energy recovery systems in Formula 1, and technologies that were talked about then was flywheel, and there's a company has developed a solution that's called Flybrid. It didn't make it to Formula 1, but it's used in Le Mans 2011. Some use supercapacitors, and nowadays most are using batteries as energy storages. 2014 they allowed a doubling of the kinetic energy recovery units, so that you could develop 120 kilowatts to balance the sport moved from 2.4 liters V8 engines to 1.6 liters V6 engines. The power unit of a hybrid is a combustion engine that is equipped with a turbocharger, and on the engine's flywheel we have a kinetic energy recovery that's a generator and electric machine. The MGU stands for motor generator unit, and K here is kinetic, and here we have another generator which is H for heat. This generator is recovering waste energy that's available at the turbocharger that contains energy that has been wasted from the combustion engine. It can be used to extract energy, but the electrical energy can also be input in here to reduce the effect that's called turbo lag. That is the additional time it takes for a turbocharger to give a response in output torque. This technology gave Mercedes in 2015 the following benefits. The power unit, which includes the engine, the electric machine there, the turbocharger, and the energy storage, they had more than 45% thermal efficiency. That is, it delivers more than 45% of the fuel's energy to the crankshaft. The efficiency is more than 50% when the energy recovery system is operating at full power. By comparison, the pre-2014 achieved thermal efficiencies of 29%, and the first iteration of the Mercedes managed 40% thermal efficiency, while they now in 2015 had tweaked it up to 45%. Some terminology used in the Formula 1 is that they call the battery energy store. The energy storage is an integral part of the powertrain and the energy recovery system. Its weight is about 20 to 25 kilogram. It's usually a lithium-ion battery, and it's allowed, according to the rules, to deliver 4 megajoules of energy per lap to the drivetrain. Although the MGU-K, the one that is connected to the crankshaft that's doing regenerative braking, it may only charge the energy store with 2 megajoules per lap. So the rest has to be taken from the thermal component that's connected to the turbocharger. The ERS, energy recovery system, is the motor generator unit that recuperates waste kinetic energy from the braking system and waste heat energy from the turbocharger. And one car has usually these two ERSs. You have the MGU-K, which is for the kinetic, and MGU-H for the heat. The ERS is capable of providing these 120 kilowatt of power for approximately 33 seconds per lap. Now MGU-H might be dropped for the 2021 season. I'm not well into the Formula 1 circuits, but what I've heard is that they were planning to drop it due to sound reasons, because it dampens the sound out of the Formula 1 engines. That would be a step back, because Mercedes said that the motor generator unit for heat provides 60% of the electrical energy that's used to power the other parts of the energy recovery system, like the MGU-K. and the MGUH contributes to a 5% increase in the engine's thermal efficiency. So this is a step back if this is implemented. To understand why we want to use these types of energy recovery systems, we look at the benefits with hybrid vehicle system. What gives hybrid vehicles benefits in terms of fuel consumption improvement? First of all, we remove the engine idle so that we don't need to idle the engine, and that's a big loss. Then we have the opportunity to do the kinetic energy recovery that I have been discussing for the Formula 1 circus. Then we have the opportunity to do load shifting. So we can, for example, take away points down here and we can just run the electric machine when we don't have high power requirements. So we don't use these points where we have low efficiency and higher brake specific fuel consumption. Yeah, we take away these points, and then when we're driving, say, up here, we do the recharging, so we're lifting the torque even a little bit higher up here. That is called load shifting, so that we avoid these points, and then when we need energy we are shifting it towards the best points. There is also another option to use the best points and duty cycle. So use the engine at a high load point, and then we turn off the engine, so a freewheel. This is sometimes called pulse and glide, so we pulse with high power, and then we glide with the engine off or with the engine decoupled, so that it works at idle conditions. This means that when we are doing the pulse, we are accelerating, we go over our average speed, and then when we roll freely or freewheel, we get access to lower efficiency. One extreme case of this is to interpret the cylinder deactivation, where, for example, a V8 engine has cylinders that can be turned off so that you use it as a 4-cylinder engine. That means that when we need to generate power, we have 4 cylinders working at higher loads than what the 8-cylinder engine would do. There is one fact about minimal powertrain energy demand, and that is if you consider the energy requirement of a driving mission, that is to go from A to B on a given time, you can prove that the minimum energy that will be needed from the powertrain is if we can travel with constant velocity over the period of time. So constant velocity requests the minimum energy from the powertrain. The reason why this is the case is that we have a convex air drag. So if we are driving slower at some point, it means that we will need to drive faster at another point. And the convexity of the air drag increases the energy demand because it's cubic in terms of the need for higher power when we drive at a higher speed. So if we have a given time to go to a given destination, then the energy minimum from the powertrain is constant speed solution. Why do we then get the pulse and glide solution? Well, the case is that we can take a little bit of punishment in terms of the total energy demand at the expense of getting a better fuel economy of the engine, especially the engine on, operating in a good point, turning the engine off. The reason why this gets beneficial is that we get more gain in the reduced engine losses. And the key message to you is that you should remember global optimum versus suboptimal solutions. To go at constant speed is good, but it might be a suboptimal solution if we have access to other features. When we're talking about energy recovery, we need to select an energy storage type, and as a help there we have what's called Ragon plots. Ragon plots are plots where we are comparing different technologies in the specific power versus the specific energy axis. The line here is the internal combustion engine, which has quite good specific energy thanks to the hydrocarbon fuels, and it has quite good specific power also due to the energy available in the fuel and the weight of the combustion engine, that is fairly compact mass-wise. Fuel cells have less energy in the fuel, so we get the part here, and that also diminishes the power that we can get out from a fuel cell system with hydrogen. We have batteries that are not at the level of fuel cells yet, but they constantly increase in power and better specific energy. Then we have flywheels, we have short-term flywheels, long-term flywheels, and we have supercapacitors. And the short-term flywheel was what's seen in the flybrid that was used in Le Mans vehicles. We have hydraulic accumulators and we also have pneumatic accumulators. Supercapacitors can deliver a lot of power, but they cannot store so much energy. The reason why they have a lot of power is that the internal resistance is very low compared to what we have in batteries and in other components. We know that weight is important from the sensitivity analysis that we did. Energy is important because energy means range of a vehicle. Power is important because power is performance. And if we want to regenerate braking power, we need to have very high power recovery. And also if we want to do an acceleration, we also need to extract a lot of energy per time unit. So we need a lot of power to do the acceleration. And supercapacitors are good for delivering that. And they can also be used for peak shaving, that we can take power peaks and place the energy in the power peaks in the supercapacitors and then move them to other devices like batteries. Now we will look at the hybrid inertial propulsion systems. We will go through the basic principles and then some design principles, and we will look at flywheels and we will model the vehicle. Before going into the details of the hybrid inertial propulsion systems, we will look at this video prepared as a demonstration of the concept by Volvo. Here comes a car that's driving with the engine, and if you look at the circle down to the right, that's the amount of energy that's stored. When you press the brake, the energy recovery system starts to store energy in that rotational flywheel, and as you can see, the rotational speeds are different between the flywheel and the wheels. And then when we want to accelerate, we take the kinetic energy and we take off and launch the vehicle with that stored energy. Some example components in hybrid inertial propulsion system is that we have an engine, we have the flywheel, then we have the gearbox, and we have a continuously variable transmission that allows this decoupling. As you saw from the video, we had a certain rotational speed of the wheels, but the flywheel had to rev up to store the energy. Then there's a clutch to decouple the flywheel from the rest of the driveline, and there's also a clutch to decouple the engine so that you can turn the engine off and reduce the idling losses. But the most critical components are that we have two clutches. We have the CVT. Another configuration that you will see at the end and that you will work with in hand in assignment number 4 if you're interested is configuration like you see down here, where the engine is storing energy in the flywheel and it's using pulse and glide. So it's pulsing in energy into the flywheel, and then the CVT together with the clutch here is decoupling the system and driving the vehicle forward. Coming to the flywheel, we have the flywheel as an accumulator, and this is an example of a design of a flywheel where we have a housing which is this round border. We have a bearing that keeps the flywheel on its shaft, and then we have a hollowing out of the flywheel. And the reason why we have this hollowing out is that we can get a higher energy to mass ratio. If we place most of the mass out at the rim, that will give us more energy per weight. So the energy stored in a flywheel or in any other inertia is proportional to the speed squared. So this is 1/2 times m times v squared in translational system, but in rotational system it's 1/2 times the inertia times the angular velocity squared. The wheel inertia we can get by integrate the area in cylindrical coordinates, and then we get this formula for the inertia of the flywheel, where the d is the total diameter of the flywheel. The hollowing out is covered by this q parameter. So this q parameter gives us the opportunity to control the inertia, and since it's q to the power of 4, it vanishes fairly quickly when q goes below 1. So just repeating the equations from the previous slide, we have the energy stored, we have the wheel inertia, and the wheel mass is given by this. And if we take the energy to mass ratio and we compare it to the wheel mass, so the wheel mass will decrease when we start to hollow out the wheel, but the energy to mass ratio will increase when we do this hollowing out. And the energy is also proportional to the rotational speed. And the rotational speed can thus become very high to store a lot of energy. When we come to the modeling of the system, quasi-static modeling, where the driving machine gives the force and the velocity, and that is transmitted to the torque split, where we are determining how much we should take from the CVT or from the engine. So there's a control action connected to this torque coupler. Depending on what action we have selected, we can tell how much this should rotate and the how much torque we'll have, and then we will have the power into the flywheel. And the modeling in this framework is then that we're modeling the rotational speed of the flywheel by studying the power that we are given, and then we take away the power losses like air resistance and bearing loss. In the dynamic approach, you have the same situation as you all already seen in the other applications, so I will not go through that one in detail, but the thing that I want you to notice is that this flywheel has high air resistance, and that's one of the reasons why the flywheel accumulator here is boxed and is usually kept under vacuum, so that you will not have that viscous air drag effect that you have in between the shell and the flywheel while it's rotating. The next component now will be the CVT. The CVT operational principle is a little bit like racing bicycles, where you are changing the gears of a front gear and a back gear. But in this case, we are not changing between fixed gears, but we can continuously adjust a primary pulley and a secondary pulley, and they are adjusted simultaneously to keep this band tight. And it has a hydraulic system to drive the pulleys and push the pulleys back and forth, so that you can get the different gear ratios. CVT modeling is fairly straightforward. You have the connection given by the gear ratio from input to output, where the gear ratio is this nu here. In the QSS framework, we come with this output torque, and we get this torque that's on the CVT, that's on the flywheel side, and we have some losses inside the CVT. Then for CVTs, while we do the changes in the gear ratios here, we need to account for Newton's second law for the two pulleys, so that we look at acceleration and deceleration on both sides. And this is one component that gives the starting of the vehicle. For example, when we're changing the gear ratio here, we're taking energy from this side and we're switching it over to the other side. And that is done with the balance of the torques here. So the system of equations gives following, where we have a change in angular velocity and we have a change in gear ratio. This gives us the opportunity to do the regenerative braking and an opportunity to store energy. Even though that the wheel speed is decreasing, we can still push torque into the system by changing the gear ratio. So when we look at the modeling, we model the losses either like this, where we have a specific loss term that we're modeling, or we can model it using an efficiency definition, and we can see how the operation of the CVT depends on loading torque or gear ratio. So with gear ratio we get higher efficiencies, and here we have how it depends on the angular velocities. Another way of viewing these behaviors here is to plot them in a three-dimensional map, where we have the input speed on one axis, we have the gear ratio on the other axis, and we have the input torque on the third axis. And the color map is the efficiency. So we see we have high efficiency here, and then the efficiency decreases when we come up to these points. So here you can look at these, and you can go back to the previous slide and see that they are matching, to see if you have understood the basic principles. With this, I think that we have come to a point where it's good to take a short break and get ready for the next part, where we'll look at hybrid hydraulic systems and pneumatic hybrid systems. So, see you back in a while.